Almost everyone building AI assumes that if you want a model to remember more, you have to hand it more text. The standard playbook is to expand the context window, feed it massive transcripts, and trust the model to sort through the noise. A recent result on the LongMemEval benchmark challenges that assumption. An agentic memory system called ZEP was tested against a baseline that stuffed the entire historical conversation directly into the prompt. This visualization compares those payloads. On the left, the full context baseline forces the model to process roughly 115,000 tokens. On the right, ZEP compressed the context down to about 1,600 tokens. The full context approach scored 60.2% accuracy. The compressed 1,600 token payload scored 71.2. That is an 11-point gain achieved by stripping away 98% of the text. The model didn't win in spite of having less information. It won because the external system actively filtered the history, throwing out irrelevant noise and retrieving only the concentrated facts required for the exact prompt. This benchmark suggests that for long-term agentic memory, accuracy depends on active data compression rather than the volume of raw text stored in the context. To understand how that compression works, we have to look at semantic memory. This is the specialized layer where an agent stores general facts and concepts, keeping them detached from the day-to-day episodic logs of what happened. This layer is a requirement for frozen weight agents. Because these models cannot learn through retraining on the fly, they must rely on an external, durable store to accumulate knowledge over time. This balanced scale UI weighs a standard document stack against a semantic network to address a common objection. The original 2020 retrieval-augmented generation paper already defined its retrieved index as non-parametric memory. Since standard RAG and semantic memory both use retrieval, engineers often view semantic memory as a rebrand of existing technology. The error in that assumption comes from looking at the database rather than the pipeline. The dividing line between basic retrieval and true memory is the presence of an active write and revise lifecycle. When you build that lifecycle, the engineering problem changes. You stop asking how to rank text chunks in a vector database and start writing logic to determine what specific information deserves to become a permanent fact. The cleanest mental model for this distinction is reading versus writing. RAG is an encyclopedia on a shelf. You pull down a volume to consult it. Semantic memory is the notebook the agent writes in and revises for itself. Vanilla RAG pulls static knowledge from an external corpus. Its only update mechanism is manual. You either re-index the entire corpus or swap out the documents. This linear pipeline maps the active write path required for semantic memory. Instead of relying on a pre-written corpus, the agent sources knowledge from its own processed experiences, feeding raw episodic messages directly into the extraction phase. Those raw messages don't just sit in a database. The system actively adds them, merges them with related concepts, invalidates outdated information, and relinks the resulting facts into a structured graph. Hybrid retrieval still happens, but only at the very end of this lifecycle. The system only pulls data back into the prompt after the raw text has been transformed and consolidated. If an architecture skips the extraction and consolidation phases and just dumps raw transcripts into a vector store, it lacks a write path. It is a retrieval index masquerading as memory. To see why that write path is necessary, consider a practical contradiction. An agent learns a fact. Maya works at Stripe. 3 months later, it learns Maya joined Anthropic last month. In a standard episodic store, both cards remain active and reachable. If a retrieval step pulls both facts into the same prompt, the agent is forced to choose between two equally weighted but contradictory truths without a clear signal of which is current. A semantic store addresses this by actively consolidating the contradiction before the user ever asks a question. Watch these data cards transform into nodes on a graph using an engine like Graphiti. It applies temporal invalidation.
The old connection to Stripe isn't deleted. Its edge dims with an expiration date, while the Anthropic connection tags as valid now. Applying these validity windows directly to the graph edges preserves the historical provenance of the data. The agent knows where Maya used to work, but it will only assert where she works currently. An agent operating over months or years will constantly encounter shifting truths. The architectural capacity to actively rewrite the knowledge layer while preserving that history is a requirement for its long-term survival. The shift towards semantic memory naturally brings up knowledge graphs, But we need to separate the hype from the engineering and define exactly when a graph structure outperforms flat vector search. Flat vector retrieval grabs the data points mathematically nearest your query. A knowledge graph functions like a city map, allowing the system to traverse multi-hop routes to connect entities that are distant from the starting point. The HippoRAG architecture isolates this difference. It extracts knowledge triples from the text, builds a graph, and then executes a personalized page rank algorithm at retrieval time to walk the routes between entities. This comparison reveals the payoff. On the 2-wiki multi-hop keyway benchmark, which requires connecting facts across different documents, HippoRAG scored an 89.1 compared to 68.2 for plain Colbert vector search. But the research paper includes a caveat. On single-step queries from the hotpot QA set, where high recall retrieval is sufficient, the graph routing only achieved parity with the baseline passage retriever. Engineers should avoid defaulting to a knowledge graph for every database. They are specialized tools for multi-hop associative reasoning rather than basic lookup. This 3D network representing the A-MEM framework illustrates a final requirement of true memory, a system where incoming information actively reorganizes the data already there. In this framework, an LLM evaluates every incoming note. It makes an automated decision to either strengthen the existing links of that note or to physically rewrite the surrounding concepts to accommodate the new understanding. This data panel details an ablation study where the research team removed those exact link generation and evolution steps while keeping the underlying LLM weights completely identical. The multi-hop performance collapsed from 27 down to 9. The temporal accuracy dropped from 45 down to 24. By isolating that single pipeline step, the data shows that the base model itself is not doing the heavy lifting. The intelligence depends on the structural organization of the data. Memory consolidation is a specific, programmable behavior driven by the external pipeline you build around the model. Write paths, temporal edges, graph routing, and network evolution all point to a single architectural philosophy. A high-functioning agentic memory is a compression system that is designed to distill incoming noise into durable, structured truth. That explains the ZEP benchmark results. It outperformed a payload of 115,000 tokens by using only 1,600 tokens of distilled facts. But this compression introduces an architectural risk. The entire system is dependent on the LLM generating the correct abstraction during the initial consolidation phase. If the model incorrectly abstracts a fact, the system creates a bad merge. That error is written into the graph as a globally reusable node, causing the agent to repeat the error across all future interactions. Semantic memory is a high-reward deployment that magnifies the intelligence of the base model while potentially enshrining its errors. That risk dictates a clear engineering heuristic. Deploy complex semantic memory pipelines only when an agent must learn from user interaction and survive shifting truths over time. For systems operating over a static knowledge base where facts are stable and temporal tracking is not required, plain RAG remains the optimal choice. The distinction between RAG and semantic memory rests on the presence of an authored retention lifecycle, regardless of the retrieval mechanism used. The AI systems that remember the best are not the ones that store the most text, but the ones engineered to decide what actually deserves to be a fact.